So, in this video, we're going to talk about our basic gas laws. So, for the first one, Boyle's law, Boyle studied the relationship between pressure and volume at a constant temperature. So, he left temperature to be constant. And what he discovered was that as pressure increases, volume decreases. Right? Therefore, this is an inverse relationship. So the formula that we get for Boyle's law is P1 V1 equals P2 V2. Okay. And then we have Charles' law, and Charles' law shows relationship between volume and temperature, which means it holds pressure constant. Right? So, if you think of, say, a hot air balloon, for example, as you heat up the temperature of the molecules in the balloon, right? So as the temperature increases, what happens to the balloon? It expands, right? And so the volume also increases. And so this is a direct relationship. And the formula here is V1 T1 equals V2 T2. So when we have an inverse relationship, we multiply. And when we have a direct relationship, we're dividing. Our third relationship is Gay-Lussac's law. And Gay-Lussac looked at the relationship between pressure and temperature, which means he held volume constant. So as the temperature increases, as we said in the previous video, right, your molecules or your particles are moving more quickly, so they're more likely to collide, and therefore the pressure is increasing because we talked about how more collisions equals more pressure. And again, this is a direct relationship, right? And so the formula would be P1 over T1 equals P2 over V2. Now, some things we have to make sure that we pay special attention to is one, that our units on the left and the right are the same, which means we have to have the same units of pressure on both sides. We have the same units of volume on both sides. For Charles' law and Gay-Lussac's law, we also have to have the same units on both sides, but we have to have our temperature must be in Kelvin. And that's because of that direct relationship between Kelvin temperature and the motion of particles. Okay? Again, temperature must be in Kelvin. So those are our three main gas laws and the relationships between our three main variables: pressure, volume, and temperature. So let's look at an example problem for each. So Boyle's law, remember, was pressure and volume are inversely proportional. So P1 V1 equals P2 V2. Right? So here we have a gas under pressure of 104.1 kilopascals with a volume of 478 milliliters. If the pressure is reduced to 88.2 kilopascals, what will be the new volume? So here we have P1, here we have V1, and then we're changing it, so that's P2, and then our new volume would be V2. All right, so we have to make sure our pressure units are the same, and they are. So we can plug those into our equation. So P1 would be 104.1 kilopascals. Our volume is 478 milliliters. And then our new pressure is 88.2 kilopascals. And then what will be our new volume? Now we know the relationship here is inverse, right? So if our pressure is going down, what will we expect to happen to our volume? Right, it'll go up, because inverse means they go in opposite directions. So we should get a smaller volume than what we started with. This is a good way, a larger volume than what we started with. This is a good way to check your work. All right, so we're going to solve for V2, so we're going to divide by 88.2 kilopascals on both sides. So our unit for kilopascals cancels, and we'll be left with milliliters. We're going to multiply and divide, so we get 104.1 times 478 divided by 88.2. and we get 564 milliliters. Now I rounded that to 564 because I had my least number of significant figures was 3. I had 3 here, 3 there, and there were 4 there. Okay. Next we have Charles' law. We have a sample of gas that has a volume of 8.98 at a temperature of 38.8 degrees Celsius. The temperature is then lowered to negative 39.9 degrees Celsius. What's the new volume? So again, if we recall, Charles' law said that V1 and T1 were directly proportional, so we're dividing those. And if they're directly proportional, then we should be able to know what we should expect for our volume. So our temperature went down. And since they're directly proportional, that means our volume should go down as well. So we should have a smaller volume than we started with. So our initial volume would be our T1, right? Our V1, sorry. And our initial temperature would be our T1. And it's lowered to our new temperature, T2, and our final volume, V2. So we plug those in, so we get 8.98 milliliters. We're going to divide by our temperature, but remember our temperature has to be in Kelvin, right? And so we need to add 273. So we get 38.8 plus 273 makes our T1 311.8 Kelvin. So 311.8 Kelvin we'll plug in here. And that's equal to V2, which we don't know, over T2, which must also be in Kelvin. Right, so we're going to add 273 to that. So negative 39.9 plus 273 gives us 233.1 Kelvin. And again, we just added 273 to that. So we plug that in, 231.3 Kelvin. Now, to solve this, we want V by itself, so we're just going to cross multiply, right? So we're going to get 8.98 milliliters times 233.1 Kelvin divided by 311.8 Kelvin, and that gives us V2. So 8.98 times 233.1 divided by 311.8. Again, our Kelvin units cancel, and that leaves us with our milliliters. And so V2 then is 6.71 milliliters, which is indeed smaller than what we started with, and that's what we expected to happen. Alright, so then we next have Gay-Lussac's law, which we said was pressure and temperature were directly proportional. And since they're directly proportional, we should see that they'll change the same direction as well. So we have a sample of gas that has a temperature of 330 Kelvin at 4 atmospheres is cooled to 300 Kelvin. So again, our temperature went down, so we would expect that our pressure would also go down. So we'll plug in. So this is our initial temperature, this is our initial pressure, and then this is our final temperature, what will be our new pressure. So we'll plug those in. So we have 4 atmospheres divided by 330 Kelvin is equal to our new pressure over 300 Kelvin. And then we'll again cross multiply to find our new pressure. So we'll have 4 times 300 divided by 330, and that gives us 3.6 atmospheres. And it did indeed go down as we expected it would. Alright. Finally, we have what's known as our combined gas law. Our combined gas law puts all 3 variables into one equation. And this is the one that's in your reference packet. So if you look on your formula page, you will find this formula, P1V1 equals P2V2 over T2. Right? Right, and also in your reference packet on the front page, you will find your STP, which we mentioned in the last unit, but here's where it becomes important, because STP is 0 Kelvin and 1 atmosphere. Okay. Alright, so let's look at a problem. If we have 50 milliliters of a sample of gas at STP is brought to 300 Kelvin and 5 atmospheres, what will be the new volume? Right, so initially we have a volume of 50 milliliters, that's our V1. Then STP, that means standard temperature, right? That's going to be our T1. And then P part means our standard pressure, right? And that's going to be our P1. Now we're changing it. It's changed to a new temperature, so that's going to be our T2, a new pressure, our P2, and a new volume, our V2. Right? And so now we'll plug them into the formula. So P1, our standard pressure, right? Since our pressure unit over here is atmospheres, we can good to use atmospheres. That's standard pressure is 1 atm. So 1 atm times our initial volume, which is 50 milliliters, divided by our initial temperature, which is standard temperature, which is it's 273 Kelvin. Sorry, standard temperature. You're probably saying, that's not what my reference packet said. 273 Kelvin. And so we get 273 Kelvin here, and that's equal to our new pressure, which is 5 atm, times our new volume, V2, divided by T2, which is 300 Kelvin. Right, so now we're going to solve for V2. Again, to do this, I strongly suggest that we cross multiply first. So we'll end up with 1 atm times 50 milliliters times 300 Kelvin equals 5 atm times 273 Kelvin times V2. And then we can get V2 by itself, right? And so we'll divide by these. 5 atm times 273 Kelvin on both sides. Okay, and so V2 will end up being 1 times 50 times 300 divided by 5 divided by 273. And so we get then 11 milliliters. Now I keep two significant figures, right, because of the two significant figures in my 5 atm here with my least number of significant digits. All right, and that is the end of this video.